Hello community! Today we have a fascinating topic. This is video 3, and in video 1 I showed you here in detail how the ring attention mechanism works if we have a ring topology of GPUs. In video 2 we discovered that the new infinite attention mechanism works here with an internal memory matrix structure that is something like a notebook. And now we are able to go the next step. Now we will develop here the ring concept further to a sliding block attention mechanism, plus the memory process. We will now have a deeper integration. Now you remember that when we calculated here how to retrieve the memory, I told you that we have here the local attention from a specific sequence or a specific block, plus we have here the memory attention from our memory matrix structure from our tensor. Now this step, now we go one step further and we integrate here the memory idea deeper into the attention mechanism itself. So this is a fascinating topic. I show you here my idea how I visualize this. So here we have 1 million token laid out here flat. And you remember we have here blocks that we calculate, and between blocks we had here memory segments, memory matrix structures that help us to summarize the blocks before. Now if we take this simple concept and we add now these new ideas from Google, and we add something like a ring cache. So we have now, theoretically, we would have a detector that flies here over our memory, over our blocks here, over our tokens. But since we also add a new feedback attention mechanism, a feedback loop is in my idea always something that is kind of a circle. So I imagine this here as a wheel running here over my 1 million token. This wheel is a new transformer architecture, a feedback attention memory transformer architecture. The wheel itself shows me here the feedback loop that I show you in detail, how we do this, how we code this, the mathematics behind it, plus the surface of the wheel. When the wheel touches you down on our 1 million tokens, now the surface area will tell us a lot about the complexity of our memory structure. So you see, I have a simple picture in mind to help me with this particular concept. But of course, if you would like to be here strictly on the mathematical side, here you have it now. This is the operational pseudocode. On the left-hand side, we have the TransformerBSWA, and on the right side, we have the brand new transformer FAM. But you know what's really fascinating? Our new TransformerFAM has now a linear complexity. This evolutional step here does also not require a quadratic complexity. But here we also have context length of more than 1 million token with this, I will not call it a simple structure, but with this advanced structure. And the idea is here simply to put here the feedback attention memory structure into the working memory of the transformer itself. So the goal here is understand here completely these two pseudocodes. So let's start. Yeah, of course, FAM, feedback attention memory, this is the goal of today. Okay, where do we start? I have in my subscriber league some grasshoppers, some green grasshoppers who start here. So the basics. You have an input sequence, and this is here uppercase I. And then you have some sequences, and this is here a lowercase a1 to a100, or whatever you have. And the transformer transforms now our input into a sequence output, uppercase O, and then we have here a lowercase o1 to, for example, o100. And this is done here by some simple formulas. Now, you are familiar with this, but just let's repeat. So we create here our query, key, and vector matrix structure. We calculate here the self-attention mechanism exactly on this structure. And for the official result for the output, of course, remember in a transformer, in the simplest case, we have here the attention block and the feed-forward block with a pre-layer normalization. Beautiful. So you see, this is all we need to know. Now, in our particular case, we need to know the block size. So how many tokens are in each block? And this is also used as the stride for the sliding mechanism. And we need here the size of the memory segment. So how many passed blocks are there that we have to put in our ring cache? But you see, basics are simple. Now for my green grasshoppers, the layer output, this is simple. As I told you, we have the attention, and in particular the attention output plus our input, and our feed-forward layer. And of course, we have here the normalization of the layer, and again, the attention output plus the input. The benefit of this particular layer output is, you know this introduces some additional nonlinearity to learn more complex pattern, has an enhanced learning capability, and we can have more complex tasks for this. Now I know some of my subscribers already asked me here, why do we put here an additional term here if we calculate the self-attention? Now, in the transformer architecture, this addition of the input term in the calculation of the attention output is something we know as a residual connection or a skip connection. And this design here is crucial for some specific reasons. And my green grasshoppers, the same works here for our new transformer, for the TransformerFAM. Maintain the continuity of the state across different processing, and especially ensures the feedback mechanism doesn't diverge too far from the original sequence context. So this was the introduction, and now to our block sliding window attention transformer architecture, our brand new structure. And now here in the official publication by Google, who invented these two new transformers, in figure 1, they give us here a comparison of the key query attention mask for the sliding window attention variants. So you see here, if we calculate attention, we can have our queries and our key matrix structure, our tensor structures. And then you have to decide a particular block size and a particular window size for your operational system. And here in A, we have the attention is restricted to the current window of 3 elements. So we have here 1, 2, 3. Always 1, 2, 3 elements. Beautiful. Then now in our new block sliding window attention, I will give you the formula in a second. We have now a block size of 2, as you can see here, 1, 2 block size, and a memory segment. Now you know, exactly like I showed you with infinite attention, memory segment 1 is just one segment here. And if we go now with 2 segments, yes, you have it that we go back now 2 memory segments. So rather easy to visualize, a little bit more complicated to write the actual formulas to compute this. So here, let's go here in detail. So in this new transformer, in this BSWA, the block sliding window attention transformer, tau denotes now the block index. Each block tau contains a set of keys and values, as we know this, determined of course by the block size. And now our attention calculating equation is modified to account here now for a particular block index tau and a memory segment M for memory. And now we have a particular notation. So for the keys here, we have the key tau minus M to tau minus 1. And this simply means this is the keys in the memory segment from the M blocks before tau to the specific block before tau, tau minus 1. And we have here the notation of keys from tau, comma, to t. This is the keys from the beginning of the block tau, block up to t. And we will refer to the transformer here as BSWA. You know this. So how does now our notation change? So if we have now the concatenation of our 2 key matrix structures, this is now key head. And the same goes for our values. This is value head. And if you calculate the self-attention, yes, you guessed it, we have now key head and value head plus our input term. Okay, so this is the basic mathematical operation that we modify now. But please note, in doing the inference, the transformer BSWA only needs to cache a fixed ring buffer size, so a block size and a memory segment. And you remember this from the infinite attention mechanism, where we had just a limited notebook. This is the same idea, of course. So therefore, it only consumes some constant memory regardless here of the generated token length. Beautiful. Now, we have now a problem that this methodology has only a limited receptive field. This means that the later generated tokens are not related to the tokens outside of our receptive fields, of our specific prompt segment. So we lose information, and we do not want this to happen. Therefore, we need a new transformer idea. But before I show you the next idea, some of my subscribers said, hey, I'm not familiar with the mathematical notation you used in your last video. So very easy. You take here this algorithm that Google published here in the mathematical notation, and then, as I showed you here in the lower right corner, this is an AI generated text. I took this as an input to any LLM system. And then I said, transform this in a new simplified pseudocode structure without the mathematical notation. So even if you're not familiar with this mathematical notation, look, this is easy. An AI system will do this for you. And you see here exactly the same. You have the input, the output. Here again, we have the input, the output. And you will see it is a one-to-one mapping here of this mathematical semantical structure, and this makes it much easier to understand, I hope, if you're not used to the mathematical notation. So no reason to stop if you say, I'm not really sure about mathematics. There's no reason that we stop now. We go on. So as I told you, our receptive field needs here to include almost everything. So how do we do this? And you know, the topic here of the last 3 videos is here a context length of minimum 1 million token. So we swap now, we add now a beautiful new idea and we create now a new transformer structure, the FAM transformer, the feedback attention memory transformer. There are now some key requirements, and this you really have to remember. The self-attention should simultaneously process now the new input context of our new block and here the FAM. FAM should be updated when transitioning between our blocks. FAM updates should compress current block information. Remember this in the infinite attention mechanism. We also said here only the strongest dominant member of the block with the highest attention score might survive because our notebook has only a limited length to store. And we have to compress this and maybe we lose some not so strong information. The same is happening here. And FAM should store compressive contextual information for the complete process of calculating here our new transformer operator. So, and how we do this? This is now what Google published. And the first time I look at this, I said, help, I do not understand here the principle behind this notation. I spent some time to understand this, and here, maybe I can help you here with. Now, either you go and you put this here into your AI system of choice, and you say, hey, write now a simplified TransformerFAM pseudocode for me. If you're not familiar here with all the details, and this is it. If you want to see this in a higher solution that you can read it on your 4K screen, we start here with the inputs, with the outputs, we define here the function, then we go on here, and you see this is here a simplified explanation. And all the abbreviation I use, like get, query key values, or normalization, or calculate the attention, or feed forward, is just what you expect it to be. Now, let me approach this explanation now from a symmetry point of view. If we look at the BSWA transformer architecture, you see we have a very particular pattern to calculate attention. We have here the concatenation here of our keys, the concatenations of our values, the calculation of the self-attention, query key values plus input, and then of course we have to take care about our feed-forward module, here with a pre-layer normalization of our attention. Beautiful. Now you will see that we have this almost identical here in our new FAM transformer. You look, we have here our keys, our values, the self-attention and the feed-forward network. This here have here a head if you want, and then we do it again. We have a concatenation of our keys, a concatenation of our value, we calculate the self-attention, and we have our feed-forward module with our attention. But of course, for the position encoding, we use here the rotary position embeddings. But please note now that here we have here, of course, some additional feedback structures that provide us here with new matrix or tensor structures in our calculation, as I told you. So as you see here, we have now our feedback from the block tau minus 1, and we calculate here specific query, key, and value feedback operators. And as I've color-coded this, so you see now here, we have here those here as additional tensors that we have here to integrate in our calculation. Let's take the first one, k hat to k hat here. Concatenation of k from tau minus 1 to tau minus 1. K tau minus m to tau minus 1. And then we have here this new term here, this new term from our feedback. And this happens here to the keys, and this happens here to the values, plus in the second operation, this happens here again. So you see, this is a very specific way of a feedback mechanism integrated in the attention mechanism. And if you think this just happened and somebody saw it, no. If you read the paper, you will find out that they experimented with quite a lot of possible variations of this formula. And they said that this is the version that was working. Again, our BSWA and our FAM structure. So this is now our new attention feedback memory structure that is the basis for the new operational transformer operator. You can go, and this is also as I show you here in the bottom right corner, this is now AI generated text. I ask my GPT-4 system, for example, here to translate this code in a simplified TransformerFAM with a symmetry. And this is what GPT-4 gave me back. So you see exactly explained what is the input structure, what is the output structure, how do we normalize these things. And then we have here our two almost identical blocks. And I've color-coded here the difference in the two blocks. So the first block here is to process the current input, and the second block is simply to update here in the attention process here, to update the feedback state that we have. And you see here our new feedback matrix or tensor structure integrated here in the classical way to calculate here the attention. And the return is, of course, the output here of the first block, the output current, and the updated feedback, so the result here of the second block. This is what is returned now by this new operation of this transformer. You see, this is it. If sometimes you don't know and it is a little bit too much at the first glance, hey, why not use AI like GPT-4 to say, hey, write me a simpler pseudocode. See if you have symmetries. By the way, GPT-4 did not detect this symmetry. I had to say, hey, look, there's a symmetry. Find it, explain it, and so on. There is something that is really amazing about this particular transformer FAM structure, because you do not have to retrain now other LLMs from scratch, but this is a plug and play option. So you can reuse your existing LLM checkpoints, because this methodology does not add any new weight tensors to our transformer layers. So this is something that is if you want an add-on, we can apply to a lot of other LLMs that we already specifically trained for our particular task. And I think this idea is genius. In the annex of the technical paper of this, I think it is page 15, if you go there, I would like to show you now another visualization by Google. And maybe this is something, if you do not like here, pseudocode notation, this is now a simplification of the processing steps. So on the left side, you have here our TransformerBSWA. And here on the main right side, we have now the operational time steps of the TransformerFAM. And what we do is we simply have here a simplification of a visualization of the self-attention mechanism now of those two transformers during inference over time. So you see the task is easy. The task is something like FAM is working good or well or whatever. So let's have here now, let's start here at the top, time step 1, and let's go down. Now here you see exactly, for example, here we are working with a memory segment size of 1. So at this point here, you see we have here our memory size and our operational block. But there's no reference now to our memory segment, let's say, -2. So how you build for your particular task here the memory segment size and the memory extension, this is a lot of hyperparameters you have to optimize. But what is nice is now the difference that you can see visually if you go now here to the other system with the rolling memory, if you want to call it. So again, let's have a look here and let's just look here at our green dots. And you see here, we go on to our green dots, beautiful. And then something happened that's not happening here. We have here we bring in something recurrent. And we bring in here from memory segment or whatever you have. You see, we stay with our 4 green dots for quite some time. We have quite some operation, A, B, C, D. And then we add our next, if you want, green dot. That is now here the letter S. So you see what's happened here is now a visualization of exactly the pseudocode notation that we just went through. If this helps you better, then go with this visualization. It is not immediately clear if you look at this. And if you have here on a later stage, you see here if you have multiple blocks with some, if you want, recurrent copy elements now, this is how it works. It is always the same methodology. And maybe this gives you a better understanding, let's say, about the beauty of the integration of the memory into the feedback loop within the calculation here of the attention within the TransformerFAM. And now just to give you an outlook, Google tells us here, well, memory and long context length is essential for any reasoning of a large language model. And they say it is hard to imagine how we can derive complex mathematical equation or logical structures without having access here to, in my words, a huge working memory. Let's say 1 million token or 16 million token length, context length. And then they say if we have solved memory, we can then tackle reasoning. Because Google argues here in this research paper, reasoning must be a phenomenon that occurs based on the current working memory. So we need to have, in my simple words, a lot of data in our current working memory to be able to have here access to the complexity of tools and the insight and the pre-training and fine-tuning of everything that happened already to be able to apply now advanced reasoning mechanisms and methodologies. But I guess more about this particular topic in my next video. But of course, I would like to show you here the original documentation, and here it is. I hope you enjoyed this video, and it would be great to see you in my next video.